Okay, today we're going to learn how to do Stokes' law, and with that we'll probably learn a little about PEMDAS and how to do equations in Excel. So here we have Stokes' law I got from a paper. So what I'm going to do is I'm going to take a screenshot of this, Shift Command 4, and it's an equation and an example. I have it from the book, so I copy it. Now I can go to Excel. I have homework 5. I'm going to insert picture from file, right? And that's on my desktop, insert. Right, so now I have this equation. Vt, terminal velocity, is equal to density of solid minus density of the fluid by 18 times the viscosity of the fluid, gravity, diameter of the particle squared. The next thing I do is I'm going to grab a little thing. This is where it came from, so I'm going to grab this link. I'll put the link here. I'm going to put this link for equation. This way you keep organized, right? The next thing I do is we're going to learn how to write an equation. So let's put this equation actually into an equation. First, we're going to learn how to make the equation with the equation editor. Then we're going to do it into Excel. This way we can actually present it. So if you ever need to write an equation in Word or Excel, if you go to text, they have an equation editor. So we're going to insert a text box. Insert a text box. And this is just for doing equations. This is not doing any math. This is for more doing equations for presentation. It's the same in Microsoft, Excel, PowerPoint, Word, etc. So if you ever need to insert an equation, right, type equation here. We know VT, right? So to start to do it, we can do a subscript, right? So it goes like this. Let me zoom in a little bit for you so you can see it better. So it's going to be V terminal velocity T equals, right, now we're going to need this fraction. Put the fraction. The first up top, we're going to need a subscript. And this is all under this equation editor. So now we're going to want to add a row, right, that's row. So if we go up here, we can click on this and we get our alphabet, right? So let's see if we can find a row, right, and that's row solid. Use your arrows here. Now hit arrow again, minus. What I would do is now we're just going to copy. See if it's better to use your arrow and your keyboard. So I can use my shift, my arrows, go over here, paste, row. That's going to be row fluid, right? That's going to be over 18. Now we're going to insert a subscript, subscript. Right, now we're going to want a mu. Let's click here. Let's see, click the arrow. Get the mu. Where is it? These always take me a little while to find. I think it's a lower, here we go, mu. Right, and that's going to be F. Could keep using the arrows over G. Then look, this has both a subscript and a superscript. That's going to be diameter. Go back up top, squared, and that's over the particle. Right, and now we have that equation. So if you ever need to present the equation, put it into PowerPoint, you can now look at it. That looks like a nice professional equation. We're going to be able to copy and paste it, etc. So let's see if now we can actually do this in Excel. We're going to try to do this equation. So what we're going to do is we're going to put the parts of it. So we're going to do the parameter name. So right, so this first one is density of the solid. This is because we're going to drop something in liquid and see how long it takes to settle. This is a settling velocity. Then we're going to do the symbol, right? Do the value, and we'll do the units. So we do this, density of the solid. Now here, this is really annoying. If you copy this, at least over here, it doesn't paste very well. So to actually find, you can sort of do it. This isn't perfect. You can do a paste special, picture, etc. There you go. And then we know it's from here. If we read the equation, this is known as Stokes' law of settling. For trying to figure out how long it takes particles to settle out. And we're going to try to figure out how long it will take a particle to settle out in the Hudson River. So we can calculate. This is the example of a glass sphere of 0.1 millimeters and fluid having 982, basically water, over density of glass. So basically saying a quartz particle, how fast does it settle in water? That's what this example is doing. Right, so the density of solid is saying 2820, and that's kilograms per meter cubed. Right, then we have the density of the fluid. Right, I'll go back, we'll grab this. I'll do an edit, paste special, picture. And that's going to be 982 kilograms per meter cubed. Okay, fix that. Let's see the fluid, right? The next part we have the viscosity of the fluid. There's different terms here with kinematic, dynamic. We're not going to get into that today. Since it's water, they're pretty similar. Picture. And this one is 0.0013 Pascal second. But a Pascal second doesn't really help us. So I'm going to see what is a Pascal. So I'm going to go over here. I'm going to Google what is a Pascal. And it's a kilogram per meter per second squared. So I'm going to put that back in, a Pascal. Put one over, equals a kilogram per meter per second squared. Right? And so if you look at this, that's a Pascal second. If we substitute in, it's going to become a kilogram per meter per second. Is how it's going to be. Or you might like it better like this. You could also do something like this, kilogram. So you know it's on the bottom. Right? So that way we'll know for when if we have to cross out units. Then we have gravity. Let's put a G, 9.81 meters per second squared. Then we have diameter of the particle. We can put this here. And this is going to be squared, so it's going to be slightly off. So I'm just going to go D for that. It's not quite exact, but I don't want to put the square in there. Right, and it's saying its diameter is, they're going to use 0.1 millimeters. I'm going to put this over here, 0.1 millimeters, but we want it in meters. So this is going to be equal to this divided by 1,000 to convert, and that's going to be meters. Right, and now look, we have everything we need to do our calculations. And we can see if we get the same answer as them. Right, and then we're going to go terminal velocity. Right, we'll try to get this in here. This one's better. Copy. See, it still doesn't work, so we're going to do edit, paste special, picture, right, terminal velocity, VT. Now let's see if we can do this. Now we have to be careful with our parentheses. So it's going to be equal to parentheses, density of the solid minus the density of the fluid, parentheses, divided by, now that's where we got to be careful. This is, I'm going to open parentheses and be 18 times, right, the viscosity, here we go, right, because they're both on the bottom. Then this whole thing times, because right now it's just going to times the tops, times gravity times viscosity. Right, and something went wrong. Let's see where we went wrong. It is, because look what we forgot to do. We forgot to square the diameter. So we're going to then square that, caret 2, and now it should work. But if you look, they did 7.71 times 10 to the minus 3. So let's convert this to scientific, put this up here, scientific, 7.71 meters per second. So now we say we can do their equation. Now let's try to figure out how long it will take something to settle in the Hudson River. So we can go back to our equations. Right, I'm going to insert a new equation, just so we have it, insert equation. Right, and we know velocity equals, put this in, distance per time, right? So, but if we know, we can calculate the velocity and we know the depth or the distance, we can figure out how long it would take a particle to settle in the Hudson River. So now we can just insert another equation, insert equation. So right now you can say time, just rearrange, equals, put in the subscript, is going to be distance divided by velocity. So if we solve, so we can do this now. So let's do this for the Hudson River. So let's look at, we're going to look at a diameter of a particle. And let's do that. So I'm going to go, I have this, show you how I'll set this up. I'll put the link in for this page, but I have different size particles here for what they're called and how big they are. So I'm going to copy this image, copy image, come back to Excel. I'm going to put this image in here. Cool, let's make that smaller. I'm going to make that smaller. Right now we can put this in here. I'm going to go back, I'm going to get this website, just so we can put this in here. This is the link for sediment size. Put this in. So now diameter of particle. Everyone's gonna pick their own unique size. So you have to do a coarse sand. I'll put diameter of the particle. I'll move this over. Particle type. Coarse sand, a fine sand, and a silt. And if you look, this is diameter of a particle in microns. Right, so coarse sand, I'm going to make one up. That's 500 microns to 2 millimeters. I'm going to do 718 microns. Fine sand is 63 to 250. I'm going to do 112. And then silt is something small, 2 microns to 63. I'm going to do 9. Now we know for our equation we're going to need it in meters, so let's convert diameter into meters. And if you remember, a micron, it goes as 10 to the minus 6. So it's equal to this times 1e to the minus 6. So that's how many meters it is dragged down, and we have those. Now we need to know this. Now we can figure out the velocity, right? The terminal velocity. So let's do terminal velocity in meters per second, right? So now, but we're going to drag it down. It's going to be a little bit trickier. So let's re-enter this. So we're going to do parentheses. It's going to be the density of the solid, but we're going to put dollar signs around that because that's a constant, minus density of the fluid, close parentheses. I give a space to give a little things. Then we're going to do 18 times the viscosity, put dollar signs. Right, now we want to do times gravity with dollar signs. And then times diameter squared. And since we're going to drag this down, we don't need any dollar signs. So that's going to be 0.39. As you should see, it's going to get smaller. And if you click on it, looks like it grabbed everything. Click on it, grabbed everything. So now, but now we need to figure out the distance. I'm going to do depth in meters. And see how these aren't great? We're going to fix these. I'm going to highlight these. I'm going to do, nope, we're going to do, we're going to do format, cells. Oh, hang on a second, I highlighted too many. Let's get these looking better. Format, cells, alignment. Let's see if this does it. Okay. Format, cells, justify. Let's see if it does it. There you go. This way you can see everything. It makes it a little bit bigger. So now depth. I have another link I'll put in. I'll put this all in the chat for you. I have contour maps of the Hudson River. So let me see. First, I'm going to zoom out. This is going to show us, here's contour maps of Long Island Sound and the Hudson River. So if we start to zoom in, we're going to look at where we're going to go sample up by Bear Mountain. So I'm going to zoom in, and we're up north of here by Fort Montgomery and Bear Mountain. West Point, Highland Park. Let's zoom in again. Fort Montgomery, we're south of Fort Montgomery, Bear Mountain. So if you look, I'm going to zoom in some more. We're going to go sample. If you see that dock right there? We're going to end up sampling from there. So now you have to, everyone can choose a depth they like for the river in meters. I'm going to choose something deep. You all choose what you like to figure out how long it'll take a particle to settle. So I'm going to choose 50 meters. You have to choose a different number. So I'm going to do 50 meters, 50, 50. Let me move these. I'm going to insert another. Move these over. I'm going to insert a couple more just to give us a little bit more room. There we go. So now I'm going to go time to settle. That's going to be in seconds. So it's going to be equal to the depth divided by the velocity. So depth divided by terminal velocity. Right? So for my coarsest one, 125 seconds, about 2 minutes. And my fine one, 800,000 seconds. I can't even estimate that. So I'm going to do time now in minutes. It's equal to this divided by 60. So about 2 minutes. Let's go down. 13,000 minutes. And let's just do time in hours equals this divided by 60 again. Just a quick fraction of an hour versus 222 hours. So a long time. And look, we can make, let's clean these all up, make it just a couple decimal places. Right, so like that. These actually got a little bit too big. Make sure a little bit nicer. And now look, we have this final thing. Let's put a little border on here to make it look nicer. Put a little border on this left side. Left border. And now look, you can see, if you look, it takes a long time for this fine silt to settle in the river. And the river's moving, it's going to be even slower, so keep on bringing it back up. So you can see why the river stays so silty. So good luck doing this. You've learned a lot. You learned how to put equations in, your parentheses, and then to get some settling time in the river. Good luck.